All right, so we can start and look at our midsem, and then we can go on to our normal discussion. Okay, so we have the problem that you're all familiar with. It should still be fresh in your memory. And so the first part of it was, so this is the diode that was given. We had said that we have a P plus N plus diode. And we had given you two files. One was IV characteristics, and the other one was, with a cross-sectional data with N, P, JP, JN, and all the these four things as a function of X. So the first one was, as we said, when you're given a data, the first thing that you should do is try to visualize it. What does the data look like, right? So in this case, what I did was, because the area was given, so I divided the current by the area to get current density. It's better to work with current density rather than the actual area. Anyway, but that's a minor point. So if you plot the current density versus the voltage, this is what it looks like, and one could see that this is log. I've plotted it on a log linear scale, so one can see that it's not a perfect straight line. One could sort of see three regions, at least three regions, and the three regions are one region here that you can see here, another region you can see the graph bending, and you can see it bending even here, right? So there are three regions, one, and maybe one can call it two, and one can call it three. At least three regions, three broad regions. Of course, you can, if you want, you can do even finer, division of the range, but at least three. And so what we can do is, we have this equation, J equal to Js e to the power diode voltage Vd by NVT. These are all forward bias. So we can try and fit this particular equation into this region here. And similarly, we can try and fit this equation here and this one also here, right? So we'll get three different descriptions of the current voltage characteristics in these three regions. So that's what I did. So in this case, the first region, region 1, is here. And so this is at around 0.65 volt, right? So somewhere here we took a point. So what I did was, around 0.65, I took a couple of points around 0.65, and I fitted a straight line, and from there I got these values. So ideality factor was coming out to be 1.00 something, so I put 1 here. So there is a region where it behaves like an ideal diode. Here, ideal diode in the sense that ideality factor is 1. This is around 0.6, 0.65. You might have taken it as different. Now, then when I go and look at around here, region number 2, so I get this equation, around 0.4. Around 0.4 volts, and of course I'm not expecting that you would take exactly 0.4, some 0.35 or whatever you've taken, it's okay. Where the ideality factor that you see is increasing, 1.3, maybe 1.4, depending on what you have taken. Not only that, the saturation current is also different here. So this is in this region here. Then the other one that I went is region number 3, where I took 0.9 volts here. So here also the ideality factor is 1.32 or so, and saturation current is this thing here, 4.6 into 10 power minus 8. So what we were expecting is, at least there is more that can be done with this particular data, right? So for example, if I look at region 3, region 3 is we have not discussed it much, but but you may know it from your previous exposure, that at higher voltages it is best to model a diode as your diode equation plus a resistor in series, right? So this is your diode equation, let's say Js e to the power Vd by NVT and all that, and plus a resistor. So one can in this particular region evaluate this R series resistance or forward resistance and all that. One can evaluate that also. But time was limited to us, and there's a lot more, so I'm not expecting anybody to have done this. Evaluate, let's say, what is the value of RS and things like that here. But at least what we were expecting is that you would do an analysis of at least 2-3 different regions, because when you plot it, you see a visible that is not a single straight line. So when you don't see a single straight line, then you should, there's no point in saying my diode has an ideality factor of Js and or saturation current of Js and ideality factor of N, right? So I mean, you should say it is in this region, this is what is true. In some other region, some other values are true. Okay, so that's the first part that is there here. All right, you can ask questions at any point. Anything related to this? Yeah, anybody has any comments regarding this particular part?
So is a log linear graph or a linear?
Log linear. Log linear, as a linear plot will give you nothing. Linear plot will just show you like this. That's all. And what do you do with that plot? In fact, as we have discussed, if you get this plot, you will start talking about cut-in voltage and all that, which we said is problematic. All right, so you'll have that issue here. Okay. Any comment? Anything?
We have done only for one region because time was less.
No, but then if you do for one, it's very easy to do for the other.
But without like time was less, we need to do 4 points. We just keep it.
4 points meaning?
Like 4 different questions.
Huh.
So time was less, so we just got it log linear and so like approximated as a one region.
The whole fitted a line over a whole, so that is not fair to do that. A huge. No, but at least you can see time is less if you write a code. Let's say evaluate ideality factor around 0.6, right? You just change it to 0.4, to 0.9. You can evaluate it at any point. And this is especially because we had given a file to you earlier how to do this particular part. Was, I mean, this is like immediately out of a homework kind of a thing. So fitting over a whole line, then the whole purpose of the data is also defeated. One single line, and you will not get a proper value also if you fit it over this. So at least, I mean, what one should see is 3 different regions. Anyway, okay. Right, now the next part is there are 2 kinds of data, right? There is a carrier density data and there is a current density data, right? So the other thing is whenever some things vary a lot, right? If you look at carrier density, let's focus on the hole density. So we've already said hole density starts here and varies so much. So whenever something is varying over orders of magnitude, plotting it over linear scale doesn't give you insight. If I just do the plot over this linear scale, I've not shown you, all that I would get is 0. It will just show 0. That's all. You will not be able to see what is happening, how is it decreasing here, all those features that are there in your carrier density profile, you cannot see anything. That's why, similarly, this is an important point, that if I take a J versus V and I do a linear plot, I don't see any feature. I don't see that there is a lower region here, which has a different ideality factor. I don't see a higher region here. I don't see any of those features. Why? Because it's varying over look at that large range. When something varies over a large range, linear plots are not very useful if you want to take a big view of the whole thing. If you want to take a view of the whole data, then, and if it's varying over a lot, then linear view will not give you the good picture. Linear plots are good for going into a specific region and focusing. Then it's okay. Let me zoom down into a particular region and look at that particular data, then it's okay. But over a large range, it will not give you insight. So that's why during the exam also I kept on telling, plot it, log, linear, whatever, plot it along different modes and see it. Okay. So now if I look at this particular data, right, so what do I conclude from carrier density data? We've already said that the structure is P plus N, N plus, right? So, and which we can immediately notice also. We can see a very high hole density. Right here, a very high hole density. And constant hole density, as you can see here, from here to here, constant, 10 per 19. So what we know is, well, P plus doping must be Na, region 1 if you would like, Na is 10 per 19. That's one conclusion that I can immediately get. The doping, P plus region doping is 10 per 19. The other one is, then we see the hole density starts to fall rapidly and then become small, which means that right at point 2, I'm just entering the junction. Then only, why would otherwise hole density fall? At a P plus N junction, we know that depletion region you've entered. So we know that we can say the junction, the first junction, P plus N, is at 0.2 micron. See, in the diagram, we have not given you where is this junction. Where is this located? So I can get that. I can see that it's located at 0.2. This thing here. Similarly, I can see if I look at electron density, I can see here a very large electron density constant. So I can say ND plus is 10 per 19 also. And we can also say N plus junction is located at right here at 1 micron. These are simple things that we can immediately, by just looking at the data, we can tell. Right, so a couple of things that we can deduce from the carrier density data. If we just simply, just look at the data and try to infer some very basic things that are there here. Now, next part is to go a little bit into detail of this. So if we see here, if we see electron, let's say if we see electron density and we look at hole density, because note that it's a P plus N junction. So we expect the depletion region to be entirely in the N region. Whole depletion region will lie, and which is also sort of visible. So where does my depletion width, so I expect depletion width to be, let's see if I have something. Yeah, so I expect depletion width to be right somewhere here. Right? If this blue region is all P plus and this region is all N, if this is P plus and this is N plus, so that we know. So I expect depletion region to be somewhere here in this. So how do I define depletion region? Depletion region is where carrier density is moving, and then, right? So I can see maybe the edge is somewhere here, right? At this particular point here. We see that electron density after that becomes constant. You enter a neutral region, hole density also becomes a constant. Electron density becomes constant, hole density becomes constant here, right? And I am just saying, maybe, I did not spend too much time going and zooming into the data and looking exactly where it is. I've just said maybe 0.35 micron or something like that, around that particular point. If you want, zoom in and you can see where the data levels off, where carrier density sort of becomes almost constant, both N and P becomes constant. You can zoom in and see where does this occur here, right? We can see it's occurring somewhere here. Somewhere here is where your depletion width is. So you could say depletion width is so much. You can argue, right? I'm not worried too much about whether somebody has written 0.3 micron or 0.35 micron. That's not too important. But yes, the argument that this is likely the depletion width of this junction, right? Now, some people may take this depletion width and say, okay, this is 2 ES by QND, VBI minus V and all that, and from there try to infer maybe doping and things like that. You could do that by using an expression, because it's a P plus N junction, and so depletion width is given by this expression here. You could try and do that, but note that You have sort of ND is also unknown at this particular point, V is also unknown, VBI is also unknown. There are a lot of unknowns here, right? So now somebody would like to say, do I know the doping here? So the other doping was very easy to find out. Doping here and doping here. That was straightforward to find out. What about doping in the middle? Huh?
Constant value between 0.4 to
It's constant value. But what is the value?
around
10 to power?
17.
It is below 10 power 17.
16, 5.
So how do we find that out? How do we? So note that we are saying this is depletion region, right? All this region is what then? Neutral. So then which I can say is rho is Q ND plus P minus N must be 0. So in a simple, if somebody has done it simply by saying the electron density here, N is equal to ND. You could do that, that's also okay. Which is fine. If you say electron density is equal to ND also, that's also fine. More accurately, you would say ND plus P minus N equal to 0, rho equal to 0. And since we know P and N at a point like this, P and N both are known, I know ND also. And it comes out to be 5 times 10 power 16. If you don't take P into account, you simply go and read a value here, you'll get a little higher. You'll get 5.25 or something like that, okay? The value of the doping here. So you know the value of the doping also. So there's no need to go and extract doping from here. This is more problematic to extract doping from this place. More direct is because the carrier density data is already given to you. So it's a more direct, you can estimate what is the doping in that particular region, rather than more convoluted. It's okay if you're trying. That's also is fine. I mean, at least you're thinking and trying something. That's also is okay. But a more direct data is available, so you can get this thing. You can get the doping in the middle region also. So, which means you're getting all the dopings. You're getting all the dopings, all the thicknesses, depletion regions, everything you're getting from this particular data. Right, but now you can get more interesting things from this particular data. All right, so let's look at. Why do you need dibilent? Huh?
To calculate tau p.
Tau p, but tau p is not related to dibilent.
LP.
LP, okay, okay. So let's come to that. So what you're saying is LP equal to square root dp tau p. Okay, so what you're saying is diffusion length, not dibilent. Diffusion length. Okay, so diffusion length. If you take the carrier density, let's see, do I have the linear electron density? Okay, I plotted electron density. That's to show you the calculation of the doping here, rho equal to so. Let me see if I have that. Okay, now before that, voltage, right? How do I estimate the voltage? Obviously, it's a forward bias junction. Currents are flowing, everything is a forward bias junction. What is the voltage that is there? Depletion width you could try, but W equal to, right? That whatever we wrote 2ES. Now that we know Q and D, VBI minus V, you can estimate some VBI also, and then from there you can try. Okay, that's one way of doing it. But a more direct again way is that note that you're given N and P, and you know right here, right, this is the edge of the depletion width. So at the edge of the depletion width, you know N and you know P, right? What is the product of the two equal to? The I know so I'm taking 30.35 as the edge of the depletion width. I know N and I know P. If I multiply them together, I get NP, and NP is Ni square QV by KT. NP is Ni square exponent QV by KT. I get V equal to 0.7 volt here, with Ni equal to, taking Ni equal to 1.5 times 10 per 10 or 1.4 times 10 per 10. So that's one way of evaluating, because you know the carrier density at the edge. Note that normally in a diode, what do? A voltage is given and you say delta P equal to Ni square over Na and all that, you do e to the power QV by KT, right? You do that. Now it's the other way around. You're given the carrier density, what is the voltage applied? So you could have done it either, you can do it in this way, or you could do it by looking at excess carrier density right here at this particular point. What is delta P? What is the injected carrier density? Delta P. And you know delta P is Ni square over Nd e to the power QV by KT. You can do that. And from there also, because we know Nd, we know Ni square, you know the excess carrier density, you know QV by KT. So you could have used either the carrier density profile to calculate the voltage, or you can use depletion width also, you can try. All right. I've not looked at which one gives you, which is more error prone and all that at this stage. Either way, if you've tried to attempted to calculate through depletion width is also okay. If you've attempted through carrier density is also okay. Whichever way you've tried to calculate the voltage that is there here. All right, so the other thing that I can calculate is this at this particular point of time, it may I'm just calculating what are the total minority charges in the my diode here, which means I'm looking at minority charge, which means note that this is P plus, this is N, and this is N plus, right? So I'm looking at what is the hole density Px here and also hole density Px here in N region. Right, and this is the total minority charge. So I'm integrating somewhere from 0.35 to 1.2, just looking at total minority holes in the N region. And similarly, I'm looking at total number of minority charges in the P plus region. So by integrating N, electron density, from 0 to 0.2. And minority charge in the P plus region, obviously you see 3.9 into 10 per minus 10. This is 2.7 into 10 per minus 8. Most of the minority charge is stored in the N plus region here. Most of the charge is there. Now, the reason why I'm calculating is to calculate delay, we have said tau equal to Q by I. And what counts is not the majority charge. What counts in the diode is the minority charge. Where are the minority charges stored? Right? So that's where I know that if I look at the total minority charge, this is my minority charge here, Q, 2.7 into 10 per minus 8. These are the total number of holes which are stored in N and N plus region here. Right? And all I need to do is, because it's per unit area, all I need to do is divide it by current density, and I will get an estimate of what is the delay that would be there in this particular diode here. Okay. Now, if you go and look at, you're talking about, I've not done that, you're talking about that looking at this particular region, right? Estimating diffusion line. So if you, now in this, if I look at this particular data, it appears to be flat, right? It appears to be constant. Now, this is not the right plot to look at how the carrier density behaves now if you zoom down into that particular region. So if you do a linear plot, if you go and linear plot in this particular region, what you would see is that if I don't have it right here, but if I were to do that, I would get a plot like this, or somewhere. Let's see if I may have. So if I were to do a linear plot, these are my junctions. I will get something like this. You will not see to calculate diffusion length and exponential like this here. Right, because the region is very, very narrow. The region that is here between 0.2 and 1 is only 0.8 micron. So if the region is very thin, you will not see a nice exponential kind of a thing. If the region were very, very thick, you would have seen a nice exponential fall. It's not. It's not a thick diode. So that's where, by looking at this particular data, it would be very hard to estimate what is the diffusion length, and from there estimate dP by tau p. You will not be able to do that. You will not. That's why plotting will show you it's not an exponential fall. So from this particular diode, from this particular data, you will not be able to get this.
Minority charge values in n region and n plus region it varies, right?
Uh-huh.
So how we take integration, like it's not constant p of x.
Yeah, so that's why I integrated. Because P is given, right? So minority charge.
How we know from how it's varying from n region to n plus region?
It's given, right? The data is given here. This is minority charge.
Yeah, I know.
Holes, right? So look at whole blue region here. So this is the edge of the depletion region. So from this point to this point, right towards the end, just integrate it. All this is minority charge because it's n region here, n or n plus. So it's all in minority charge. Just integrate. That's what I did. Okay. So let's look at we'll come to this carrier density profile in a minute. So let's look at the current density. So this is the current density. Current density data, right? So again, this is our Jn and this is our Jp. So the current density data is also quite sort of looks strange. It's not a standard current density, but note that Jn and Jp are given. If you had summed up Jn and Jp, you would have seen flat, constant current, right? Jn and Jp, if you just add them up together, you know the current flowing in the device is always Jn plus Jp. Just add them up together, you'll get this. So you know the total current flowing in the device, 10.2 ampere per centimeter square. So that's the first thing that you immediately get. What is the net current flowing in my device? Now the next part is now what do I do with this particular data? How Jn is going in a particular way, Jp is going in a particular way. What can I extract from here? This information that I get. So let's take one of them one at a time. So let's analyze note that minority carry a whole current in this thing here. So let's analyze, note that this is P plus, this is N and N plus. So let's look at in this region, whole current, minority carry a whole current. So we are focusing on the red one here, right? So we are focusing from this region onwards. Why are we focusing in diodes in minority carrier currents? Because minority carrier current is much simpler than a majority carrier current. We had discussed in detail, a majority carrier current has diffusion, drift, it's very complicated. Minority carrier current is much simpler. It's mostly diffusion. That's it. So it's only one component. So if I start from here and look at this region here, from here to here, what do I see? I see a certain amount of current here at this particular point. So holes are being injected, right? What do I see? If I read the value, I see Jp 0.02 is 4.06, right at this particular point. Then I come to at this edge. I read the value here. I see Jp1 is 3.4. At 1 is 3.4. Jp at close to this thing I've taken is 2.42. Right? These are broad features. The amount of current that is injected is 4.06. The amount of current which reaches this particular point is 3.4. And the amount of current which reaches this particular point is 2.42. What is happening? 4.06 minus 3.4 tells you what? Holes have been injected in N. What is happening to them? They're recombining. So 4.06 minus 3.4.65 represents current due to recombination within the N region. That's the recombination current, right? So much was injected and so much came out at this particular point here. What is the difference between the two? It's a recombination current. That's why I had given you the continuity equation also. If you apply continuity equation, del Jp by del X is minus Q into R. is recombination. So you can get what is the recombination rate in this particular region. You know the two ends of the current. So you know how much is the, if you just integrate this, you will get the recombination, total recombination current. So I'm not expecting you to, there's a lot that you can do. You can get recombination lifetime and all those other things that are there. What you are trying to get through diffusion length, not through diffusion length, but looking at this data here, how much of recombination is occurring. From there you can get. Right, so so this is so if I look at the data, I know now the difference between this current and the difference between this current is the recombination current that recombine. Now, interestingly, now what happens here? Look at this one here. There's a small region and the current is dropping here. So current is dropping, again recombining. If the current is reducing, why else would the current, if you look at the continuity equation, look at this continuity equation. We are talking about steady state, so this is 0. So forget about this. 1 over q del Jp by del x plus G minus R. There's no generation, no optical, so forget about this also. So why does the current change with position? Due to recombination, that's it. Right, so here also recombination is occurring. In this region, current is changing. But the entire current does not recombine, it flows into the contact. Right, so a part of the current just flows into the contact, 2.42. But the difference between 3.4 and 2.42 tells you the recombination in N plus region here. There's something recombining in that, even though the region is short, but what happens is maybe the lifetime is much lower in N plus. Lifetime is much lower, so it's recombining here. Look at the profile here. If there were no recombination in the N plus region, it would have gone like this. It would have been constant, because if no recombination, then del Jp by del x is 0. Nothing changing. Right? So now if you want to interpret what is this 2.42 here, 2.42 is what is flowing into the contact. So 2.42 is diffusion current. Everything is diffusion of holes collected at the cathode. So if I look at this particular region here and I zoom in and look at the carrier density, look at how the carrier density looks like. Hole density in that region. It looks almost linear. Linearly going. So this looks like a short base diode that we have discussed, where carrier densities go linearly. And if I calculate from this here q dp by del p by del x, I get some 2.62 and the actual current is 2.42. So I come close to that. So this is what is happening here. It's as if the current, the holes that are injected from here, they come here and they go into this particular region, and this region itself is acting like a small short base diode kind of a thing here. Current is flowing like this here. See? Almost linear. Carrier density profile is linear. So if you want to understand what is this 2.42 current here, where is this coming from? It's nothing but a diffusion current that we can calculate here. Q dp del p by del x. So if I take the slope here, the slope is given here. This is the slope. This is the charge. And in the n plus region, we have given you the mobility. Mobility multiplied by kt by q gives you the dp. So q dp, and this is nothing but del p by del x by taking the slope here. And so it's nothing but a simple diffusion current, which comes out to be 2.62. But note that the current is actually, is flowing. So there is a current is reducing. Those recombination is also occurring. So it's not a simple here. So now something similar is what we can do for the other side also. For the other side, minority electron current. So now we focus here on this part. So the current at this particular point is 6.13. The current that reaches the contact is 5.24. So 6.13 minus 5.24 represents recombination in the P plus region. This 5.24, which is flowing into this, is due to diffusion of electrons to the anode. So again, if I go and look at carrier density here, look at that, it looks linear. And so I can say q dn del n by del x, and I can calculate, and it comes out to be very close to that here. So this part is also like a short base diode. This one here, the carriers that are injected here. All right, and the minority charge we had already calculated, total current we have already calculated, taking the ratio comes out to be delay about 2.7 10 per minus 9 second here, about 2.7 nanosecond. So if we were to switch on and off the diode, we may expect delays to be of that particular order in the nanoseconds region here. Right, so these are there are lots of information here. Now, I'm not expecting that you guys are just starting. I'm not expecting that you would analyze everything. Of course, that is there. But, are you looking at the data and at least wondering, why is the current reducing? I mean, are you looking at it and even the first thing is asking a question, why is the current reducing? Why is this current reducing here? So if I look at this one here and this one here, your answers may be wrong, let's say, right? But are you asking the question? By looking at the data, are you asking the question, why is JP reducing? What could be the possible source of JP reduction? Why is JP reducing here? What could be the possible? Right, so I mean, as I said, I'm not expecting that time is limited and lots of other things are here that everybody would have done what I'm pointing out. But these are some of the things that one can sort of, looking at the data, one can extract from the given data. NP, JP, JN, some useful information that we can get from this. All right, comments. So what all did you get from the current and carrier density data? Apart from, I know a lot of people, I just glanced through it, got the dopings, thicknesses, right? So those are okay, doping and thicknesses. Beyond that, were you able to get anything? Beyond doping and thicknesses? Huh? Voltage? I think some people have done voltage, tried to extract the voltage. Huh? Built-in potential, how do you get that? VBIS? Uh-huh. NAND by NI square, okay. All right, so you can do that, except that this equation does not apply to P plus N. When once this equation applies to PN junctions, not P plus N and that. But okay, yeah, built-in voltage also you can get some, at least is, I mean, yeah. So that's one. What else? Built-in voltage, aside from built-in voltage, what else can we get? And anybody who did something else in this? Diffusion coefficients, I gave you mobility right in the beginning, right? All the mobilities are given. So all you have to do is multiply it by KT by Q, right? So that's sort of, I would say, trivial, because mu P is given, so dP is sort of trivial, right? So anything else that somebody attempted, tried to calculate from the carrier density, something that I'm missing? See, this is how the whole electron density, if I plot it on the linear scale, so this is how it looks.
Accumulation region between N and N plus.
Can we assume?
Like the region between N and N plus.
N and N plus. Yeah, there is you can see this region here between N and N plus, right? So carrier density is rising, electron density is rising like this here. Look at, can people see this? There's an interesting part here. The holes have been injected, right? The holes they look like this, and it seems there's a sharp reduction in the hole density as you go into N plus. Why?
Accumulation.
Huh?
Accumulation.
A reduction, why would a reduction be accumulation?
N plus N, phase.
So you're going into N plus, why is the hole density sharply reducing? What's the reason for it? Look at that here. Your n, it almost looks like, and you can see it here, right? I've not plotted, but if you plot hole density, you would see constant and then reducing. Why is it occurring here? Sharp reduction in. By the way, is this a depletion region here? Yes or no? Here. Is n plus region, n plus junction, what kind of a junction is that? It's not a p-n junction where carriers are depleted and all that, so it's not. What happens at an n plus junction? N plus could be, n plus you can think of it like a metal maybe. But metal semiconductor junctions usually have depletion. Usually have a depletion region associated. Huh?
And accumulation also.
Accumulation also you could get under, depending on what you, this thing here.
Depletion region depend if it's a like Schottky type of.
True. So anybody wants to take a this thing, a educated guess, not a random guess, why this is reducing? What is the reason that the holes that you have injected, the moment they come to n plus, they are sharply declining? What reason are they sharply declining? Which is the sharp decline. That's another way of saying concentration gradient and sharp decline is the same thing. Why? The question is, why is it occurring?
Recombination due to diffusion.
At n plus region, electron concentration is very high. That's why hole will recombine faster.
Okay, so recombination in n region, if you look at it, it goes as R goes as delta P by tau. There is no n anywhere. Once the electron density is above a certain level, it doesn't matter. There is no dependence on n. But yes, what may happen is lifetime may become small and all that in n plus. But note that those kinds of decline occur over a larger range. This is where you are seeing here, right? You see this decline and all that, right? This is a very sharp decline here. Sharp. Note that it's almost like this, sharp decline. This is also like this, somewhat like this, sharp decline. So what I would suggest is, what you do is, to answer this question, n, and this is n plus. So you already know that this is 10 power 5 times 10 power 16, and this is 10 power 19. Draw a band diagram here at n plus junction. Draw a band diagram and see how it looks like. Can you guys attempt? Take out and try a band diagram. How will a band diagram at n plus junction look like? Okay, so let's attempt that. Band diagram meaning you'll draw it like this. So there is an n. Both are silicon. So you start off, as you know, the band diagrams are drawn by going and drawing E0. Both are silicon. In one case, let's say the Fermi energy is here, and the other case the Fermi energy is almost here, coinciding with this, right? And this is, as you know, electron affinity, and this will be the work function here, and so this is n, and this is n plus. Let's just say, for the sake of argument, this is let me just calculate how much for a 5 times 10 power 16 doping. How much do I expect here? Can people calculate? What is the difference between EC and EF? What is this likely to be? This is likely to be KT by Q ln KT ln the carrier NC by N. NC by N, carrier density. So KT is 0.026 ln NC is about, huh?
3 into 10 to the power 19.
Okay, 3 into 10 power 19, and this is 5 times 16. So we have now, let's do the calculation. ln turns out to be 0.16 or something, if my calculation is correct. 3 times 19 by 5 times 16. All right, so let's just take it as 0.2, approximately 0.2. So how will it look like now? Band diagram. This is before equilibrium. But by the way, why do you start band diagrams like this? First you take n separate, n plus separate, and all that. What is the basic idea behind this?
Equilibrium is familiar with sugar and
No, that is there. But if you try to, this approach, you try to generalize. It's not about band diagram. You want to understand something. What do you do? If I give you something, if I, tell me what is there in this remote, what would you do? No, you want to understand the remote. What would you do? Huh?
open it
Open it and break it, right? You separate out the parts. And then what would you do? Try to assemble it back. So this is the same thing, right? You want to understand the final band structure. What are you doing? Take the elements, different elements that are there, separate them out. Here is n plus, here is all this, right? All of them separate. Now let's reconstruct the final band diagram by bringing them together. Right? It's the same approach that you're doing. What you would do intuitively to try to understand, break it up and put it together. Right? That's a basic mechanism for understanding anything. Break it up and put it together. So that's what we are doing. Break it up and put it together. Right? So now what do you do with this? What is the next step? How do you put it together now? We have broken it apart. How do you put it together? Fermi level is the same everywhere. So that's the first thing that you draw. Then draw the interface. Let's say the interface is somewhere here. Then? Huh? Yeah, a little bit away from the junction. So what happens a little bit away from the junction? Conduction band would be right here. Correct? A little bit above maybe. Anyway. Right, so let's draw Fermi energy. And let's draw the conduction band. Conduction band is a little bit, let's say here. And conduction band, let's say far away would be somewhere here. Right? And then how will it go? Obviously smoothly connected. I mean, we're not going into the details, so you will go like this. This is how EC will go. Oh, sorry. What did I do? I just the other way around, right? Here. EC would be start from here. Right? That's how EC will go. And then EV will also go like that. Right, so this is what you would see. And what would be the total this thing? Roughly 0.2. Because this is 0.2, so there's also 0.2. So now a hole comes in here, right? From the left, remember the hole is coming, hole is here. What does the hole see? The hole sees a barrier of 0.2. And so note that if the hole sees a barrier, if the hole density is px here, the hole density here is going to be px, or whatever. Let's say the hole density is p0 here, the hole density here will go p0 e to the power minus 0.2 by kt at this particular point. That's what is happening here. The hole immediately when it comes to an n plus is seeing a barrier. So it's not recombination which is causing the hole density to drop. Is that right? At the junction you're forming a small barrier. And that's where it's causing a sharp drop in the carrier density here. It comes to this. After that, there is no barrier. Then it goes in its normal way. It diffuses and recombines and all that. But here is a junction region where it's falling so rapidly. That is going in this particular manner here. Right. So where is this current density? Yeah. Exactly. This part here. Okay, any other comments? Anything, any clarification? Anything else regarding the midsem? Midsem was easy or tough?
Easy or time?
Huh?
Time was
Time was limited to do that. Okay. Okay. All right. So then let's see how much time do we have for today. So a little bit of we can start with the, or you have questions. We can discuss more on this. Any other clarification regarding this? Anything that bothered you in this particular data? Why is this like this and all that?
Sir, about the delay calculation, can you just repeat?
So delay calculation, we said delay in a diode. Our discussion in the diode was, if you look at, let's say, P plus N diode, right? So in a P plus N diode, we said delay is delay. We have been saying as charge by current, charge per unit by. So the next thing is to find out what are the charges. So charge, as I've said, is actually made up of two charges: junction charge plus a diffusion charge. There are two distinct kinds of charges in PN junction, bipolar, and even in a let's say a MOS, a junction charge and a diffusion charge. So junction charge is all this depletion region here, and this charge, so delay would then be, one component would be Qj by J, and another component would be Q diffusion charge by J. So the first component we've said is like it goes as Cj Kt by Q by current density J. It can be written in this particular form. The next component is in a diode like this, maybe long base diode, long base that is there, this comes out to be lifetime. But if it's a short base diode, then it comes out to be W, whatever is the thickness, WB square over 2 dP kind of a thing, it comes out, short base. This is long base. But general thing is what? We have to find out the diffusion charge divided by current. And what is diffusion charge? Diffusion charge is all the holes that have been injected here. Holes in N. Right? Holes in N, which is basically minority charge. So that's where when I did the calculation, I ignored this particular part, Qj by J. You can add that also in delay. In delay calculation, you can say, note that we have an idea about the junction capacitance also. If you know the depletion width, you know the junction capacitance, you know the current density, you can add this up. You can calculate here. In fact, I have not done that. You can do the first part of the delay calculation also by estimating depletion width, multiplying by Kt by Q, and you know J also. So you will get that first component. The second component is where I was concentrating. What is this second component of the delay? Diffusion charge. And so that's where I said in the N, and since we have N plus also, we said integrate the whole thing. Total charge, that is the Q, and divide by the total current. So that's where I just took Q and equal to Q, Px, dx, starting from the junction, x equal to 0, right up to the contact, just integrate it. Junction to contact. And get the whole charge, all the minority charge that is there. Of course, there's minority charge here also, P plus also, but that's much smaller. And get this part of the delay here. This is an important point. Once you do the calculation of the delay, add this, it may turn out to be that this is more than this. So we are not really limited by the second component, but we are limited by the first component. It may turn out to be in the delay, because the delay depends on at what current you are operating. We have discussed this many times. If you go to very high currents, maybe then this term becomes negligible and you're limited by the second one, right? But in the present this thing, we should do the calculation of this also and see where are we. Roughly maybe depletion width is around, let's say 0.1 micron or so. Depletion width is this, and Cj will be equal to epsilon by 0.1 micron multiplied by area, or area is not needed because we are doing J, and we can do that. We can calculate that also. So there are, note that all these analysis will require, there are not too, in semiconductors there are a handful of concepts. It's not a large number of concepts that are there, and you have to, that there are some 25 equations and things like that. There are, that's where I gave a set of equations, right? There's a Poisson's equation, there's a continuity equation, there's a diffusion equation, there's recombination. Maybe, I don't know, I think a lot of analysis, a lot of insights you can get maybe with a set of, let's say 10 equations. But you have to know now how to apply those 10 equations to a given data. How do you apply, where do you apply those 10 equations to extract meaningful information from the data that is given to you. Continuity equation is one that we have used here. Poisson's equation is not too relevant here. If you just look at all the analysis that was done, how many equations have we really used? What have we used really? We have a basic diode equation calculating N and Js. That's it. Not much. Analysis of here is hardly any equation for all this data. Analysis of this, yes, we have used maybe neutrality condition to get the doping. We have used a basic equation. Most people are, if they remember this, NP equal to Ni squared. That's only equilibrium. When you go beyond equilibrium, then it is Ni square e to the power EFN minus EFP by KT. It generalizes to this equation. What is the difference between the two quasi-Fermi levels? And in a PN junction, EFN minus EFP is equal to QB. Right? So that's a very, very important fundamental equation. NP equal to Ni square generalizes to NP equal to Ni square e to the power EFN minus EFP. The next question is, what is the difference between two quasi-Fermi levels? That's equal to QB. Either you know this or you know this one here, delta N equal to or delta P equal to Ni square over Nd, which all of you know, e to the power QV by KT. These are very, very simple fundamental equations for a PN junction. So you use that. The other one that we have been using is introducing that if you want to estimate delay, do the Q by J. Use that. Then the all other interpretations that I have done is based on looking at this continuity equation. Okay, if a current is coming in and if less current is going out, what happens? Well, it recombines. That's all one is using. So one is analyzing and trying to understand. So you may say, what did I extract from here? Well, it gives you an insight as to this much went in, this much came out, 4.06. The difference is recombining. Why is it recombining? If you want to ask further question, the difference 0.65. Why is there a loss of 0.65? Why isn't there a greater loss? So that will, the answer is from here, Q into R. So if you want to know, note that del Jp by this, so this continuity equation minus QR. So if I take a region and take a region x1 to x2 and I integrate this from x1 to x2, right? And so this will give me Jp x2 minus Jp x1, the difference of the two currents, and that's equal to recombination. Now the issue is, okay, so this much is recombining. The next important point is, how do carriers recombine? What is the model for recombination? if you want to go further now, so this much you can get from continuity equation. How do carriers recombine? So when you write continuity equation R, note that the next step is you need a model for R, and the model for R is delta P excess carrier density divided by tau. So if you now go and you say delta P by tau, so now when you are integrating and you put delta P by tau, you can get, assuming tau to be constant, you'll be able to get tau also. You will understand why is it changing so much, because there's a recombination lifetime. So it's the same, the number of equations and all that are not too large. It's a small set of equations, but you have to apply it and work with them and try to apply it and extract as much information as possible that is there here. Similarly, when we look at this particular one, so then one has gone into this, why is this current going like this? What is happening to the current here? To trying to understand this particular region, looking at carrier density in this particular region, seeing that it's linear, and keeping in mind that the minority carrier current is predominantly diffusive. The drift component of minority carrier current is negligible. That makes the whole analysis much simpler. Do not try to analyze majority carrier current. Majority carrier current, if I were to look at Jn, Jn will have not only Q dn, del n by del x, but it will have Qn, mu and E, even though E may be small, but because n is so large, that is significant. So now you have to go and look at the small amounts of electric field. It becomes much harder, much harder to look at what is really happening to Jn. In all these devices, don't look at Jn. This is one of the things about both bipolar and diodes and all that. If you want to understand, yes, Jn is flowing, but if you want to understand, focus on the minority carrier currents. Hole current in N region, electron current in P region. Focus on them, and then you will understand what is going on. Ignore the majority carrier currents for understanding it. Right? Because, and then it becomes, you focusing on that, looking at how things are changing, will tell you, why is it going like this? What is the reason? And all that. Okay, all right. So let's we'll stop and I'll show you a few more things, and then we'll huh?
Why did we take dp by dt as 0?
dp by
dp as 0 in continuity equation.
oh here let's see, where are you? Why did we take this 0? Because it's all steady state. Nothing is varying with time. It's only when you apply a voltage as a function of time, or if you're switching on or off light and all that, then things change with time, right? So most of the discussion, all that we do is DC. And DC, nothing changes, right? So that's why we put del P by del T 0. DC situation.
Even though in the steady state there can be recombination condition.
Yeah. Okay, so what is the meaning of steady state then? What is the meaning of steady state? Steady state, a simple meaning of steady state is DC. DC condition. So in DC condition, what do we mean? Del V by del T is 0, del I by del T is 0. All this is 0, right? Nothing is changing. Current doesn't change with time. Voltage doesn't change with time. In DC, it's fixed. Everything is fixed. Right? So in steady state, the basic definition of steady state is no matter what you take, del by del T of that is 0. Anything that you take, any X could be anything. P, N, whatever. J, JP, JN, everything is 0. Derivative with respect to time is 0. That's the basic definition of DC steady state. That's what, otherwise note that continuity equation becomes much harder to solve. In fact, I doubt you have seen any example of continuity equation where both this term and this term are non-zero. Then you get a partial differential equation, because then P becomes a whole density and all that become a function of both x and t. So P, when it becomes x and t, it becomes a fairly difficult problem. So for example, if you take a PN junction and you say suddenly I switch the voltage from forward bias to reverse bias, right? And I'm looking at the transient. The solution is fairly complicated. It's not easy. So all the time we look at simple things, steady state, or if you look at transients, then in transient what you will do is there is no variation in whole current with x. You look at that specific situation. So what happens is this term goes to zero. So you again get an ordinary differential equation, only in time. But if you get a partial differential equation both in x and t, then you're done for. I mean, you'll have to go to numerical calculations and all that, much harder problem. And you will hardly find anybody doing that. Modern textbooks will completely ignore it. In old textbooks you may find some discussion. Modern textbooks will completely ignore it. You will hardly find any discussion of those kinds of P as a function of both x and t. You will not see that. So that's steady state. And equilibrium. So equilibrium is what? Equilibrium is not just steady state, del x by del t equal to 0. That of course steady state is a part of equilibrium, but also that you have all the JPs, JNs, all those are also 0, right? No net hole current, no net electron current, no external excitation. All those other things are also. You have a EFN equal to EFP. One single EF characterizes the whole system. Basically, the electrons and holes are in equilibrium with each other, right? Note that when the electrons and holes are not in equilibrium with each other, that's where you define a separate EFN, a separate EFP. Electrons exist by themselves, they are not in equilibrium. Holes exist by themselves, not in. So you do all that. And another interesting thing about an equilibrium is every process, if there is a process which takes a system from A to B, something that is happening which is going from A to B, it will be exactly balanced by another process which takes a system from B to A. Exact balancing act will be there. So when I say JP is 0, if diffusion is causing holes to go in this direction, drift will come in and cause holes to go in the other direction. Drift and diffusion will balance each other. That's where you get JP equal to 0. Similarly, Jn equal to 0. If there is a generation, then there is a recombination, the balancing. So what you see is what people call it is a detailed balance. Every microscopic process that you will see, that if it's going in one direction, there's another microscopic process which causes it to go in the other direction. Like, you guys have seen reaction A plus B go to C and then C goes to A and B, right? So both the processes are there. A plus B is going to C also, and C is coming back to A plus B also, and the two are exactly cancelling each other. So as you examine equilibrium, you will find these things microscopically, that this is what is happening. When we say current is 0, if I take a conductor and I take a cross section and I say, okay, it's equilibrium, J equal to 0. But what is happening? Electrons are going here, but electrons are going here also. Electrons are going from left to right, but electrons are going from right to left. It's not that the electrons have stopped going from left to right or right to left, right? But they are cancelling each other. So there is a cancellation process that is going on. And that's how equilibrium is attained. Equilibrium is not absence of things, but a perfect cancellation. Generation being cancelled by recombination, drift current being cancelled by diffusion current. There is light is falling on my semiconductor, right? So absorption is taking place, but emission is also taking place. So all these things are constantly cancelling. A perfect cancellation is occurring. Okay, so I think let's stop here. We'll continue with MOS when we return back. Okay.